Okay, let me start. I think you all know about this, but I'm going to say it again. So we have a midterm on Thursday. We have another room for the midterm because otherwise here it's going to be too tight. It's not easy to get another room, I can tell you. So here is the other room. So the other room is in a building called LSRM, which I put a map here for people that it should be about 2.5 minutes walk from here. This place, Lab for Research on Structure and Matter, so it's 33 and Walnut. Go down Walnut, turn left, should be there. The room is called AUD. Should be almost as large as this one. So people whose names start with A to K, including K, should go there. Yeah. Last name. Okay. Okay, I'll change it later. Last name. That was the question? Okay, last name. Go there. I think there are around 64 of you. And the rest will be here. Please don't be late. Oh, wow, this is amazing. So I'll move it. Okay. I know that I don't need to tell you not to be late. You tell your friends that are late that they shouldn't be late to the exam because it bothers you. Closed book exam, so you don't need anything except for a few pencils. We put 3 practice exams on the website. The TAs will discuss them in the recitation if you want to discuss it or other things. Reminder, the recitation moved. They are now, starting today, I think, Moore 2016. Today 6:30, tomorrow 5:30. So please go and ask questions. Yes?
There were some problems on the midterm exams that covered some material that I'm not sure if we've covered, so like shattering.
You'll see today. But yeah, so as I said last time, I'm going to say again, so this is the first time this class is being taught. There was never an applied machine learning class, so the exams are approximate. That's what I can do. 2 exams are from previous versions of 5.19. The material overlaps largely, but it's not exactly the same. Still, it will give you an idea. 1 exam is from a class I taught before. Again, doesn't completely fit, but will give you an idea of what kind of questions we're planning to ask. That's the best we can do. Hopefully, it will give you an idea. As I said, it covers everything we touched in class and in the homework up to the end of today. If material appears in the hidden slides, it's not covered. This is there just for your enrichment. Only things that I covered and discussed in class or were part of the homework. I think there will not be any gray area, so you shouldn't worry about it. Okay, any questions on that? Okay, so homework 2 plus the 1 Slack day is due tonight. I know that a few of you wanted more Slack days. The reason I wanted to do it only with 1 is because I don't want you to work on the programming assignments until the exam. I want you to spend some time reviewing the material. And I know that students have to be forced sometimes to do something because otherwise they'll be greedy. I think that's better for you. My office hours, to remind you, I've moved it and it starts only at 5, both Tuesday and Thursday. Questions? No questions. Okay. So let's move on. Okay, you saw this map, you know where it is. Okay, so that's, last time we talked about PEC learning, and the final example the one and final example that I gave was for this class. I just want to remind you without the details, we showed that this is a class of function that is PEC learnable. The way we went about it is there were 2 steps. Step 1 was determining how large is the hypothesis space, how large is the class of function of all KCNF functions. And we decided that the log of this class is order of n to the k. K is a fixed number, so it's polynomial. So from a sample complexity perspective, it's PEC learnable. This was step 1. Step 2, we need an algorithm. So in step 2, we developed an algorithm to how to find a consistent hypothesis. We developed an algorithm that, given data, can find a hypothesis that is consistent with this data. And the way to develop this algorithm involved some important ideas that we talked about earlier. Specifically, it involved blowing up the feature space. And I chose this example deliberately so that you'll see that this is a key concept. We also talked in the last few seconds about the fact that this illustrates another point, which is that the distribution-free notion that is part of the PEC learning definition is actually important because once you transform the feature space, you actually change the underlying distribution. And if you somehow developed an algorithm that works on one single probability distribution, say only over uniform distributions, this would limit you in general. And therefore, it's good to have a theory that is distribution-free. Okay, so this was one example, the only example. There are a few other examples in the hidden slides if you want to consult them. I'm not going to talk about it more. I want to finish with PEC learning just saying that the theory, among other things, tells us something about learnability. It can also give negative results. One can use it to show that some classes of functions are not learnable. And you can talk about it both from the complexity theoretic. It's just too difficult to find hypotheses that are consistent with the data. And from the information theoretic or sample complexity perspective, the hypothesis space is just too large. So you cannot learn. So I'm not going to go over the example. I want to move over, and these are the 2 important points that I want to talk about today. One is something that we kind of discussed a little bit, and justifiably, you were concerned about the fact everything I talked about so far had to do with a function that is completely consistent with the training data. And for these kind of functions, I show that if we manage to find a hypothesis like that, it's going to do well in the future as a function of the size of the hypothesis space and so on. But that's a little bit too strict, because what if I'm almost consistent with the training data and not quite consistent? So we want to generalize. And the second thing that we want to generalize is everything we said so far had to do with the finite hypothesis spaces, so we want to generalize that. So let's start with the first one. And the notion is called agnostic learning. But basically, it's exactly what you were hoping for. So assume that we're trying to learn a function f, a concept f, and we are going to use a hypothesis in capital H, even though f itself is not in H, which means it's outside H. It's more expressive. So immediately we know that there's no member in H that is going to be consistent completely with f. Now, it could be consistent on the training data, but in general will not be even consistent on the training data. So a more realistic goal is to try to find a hypothesis H in capital H with small training error. This is the training error, right? Nevertheless, with this small training error that is non-zero, as we had last time, I want to be able to guarantee that it's going to be good in the future. So I want to guarantee that this true error, the error on the distribution, or the probability under the true distribution that f is different than h, is going to be small. Okay, so this is really the true goal of learning, right? What you see here. I want to guarantee this, right? That's the behavior in the future. And all I know is what happens here. What's my empirical error? And hopefully this is small. So I want to say something about the gap between this and that. Everyone agrees with that? That's really our goal. So the mathematical tool that I'm not going to prove, but I just want to mention that is used here is something that is called Hefting bounds, that really talks about this deviation between the true probability of some event versus the empirical probability of some event. So imagine that you have a coin. I looked before the class and I couldn't find a coin. So imagine I have a coin here. This coin has some true bias, head and tail. Let's say it's 0.6 head. I'm going to flip it 1,000 times. The true probability says that 600 of them should be head. It's not going to happen. I'm going to measure something. And as you expect, as a function of how many tosses I'm going to make, the gap between the true bias of the coin and the number of heads, or the fraction of heads that I observe, is going to go smaller and smaller, right? That's exactly what we are doing here. So really, Hefting bound says that this gap between the empirical error, the number of heads that I got when I toss the coin, and the true one, the gap, the epsilon, is going exponentially down with epsilon square and the number of coin tosses, which is good, right? Really the best we can hope for. Now, this is exactly the scenario that we have in learning. The empirical error is what you observe when you saw a lot of examples, you found a hypothesis, and you see how many errors your hypothesis makes. And the true error is what you will see in the future when you run it on a lot of data. So the gap between these two goes down exponentially in m, the number of examples, and epsilon, the error that you will incur. Okay. So what do we want? We want this error, as before, we denote this error as delta, and we want this to be small. And now that we want this to be small, we can isolate, as we did before, we can isolate m from this expression and say, okay, if we see these many examples, it's going to be small. And we can also isolate epsilon from here, and we'll see what is the gap between the true error and the empirical error. So when I isolate, I'm going to save the algebra from you. It's the same algebra that we've done before. If I isolate epsilon from here, that's what I get. I get the true error is bounded by what you see on your training data, the empirical error, plus something. This is the epsilon. And this something behaves as you would expect, right? So it goes down with m. More examples, less error. It goes down with delta, larger delta. This is going to be smaller. And it's proportional to the size, the log of the size of h, which is, again, something that we've seen before. The more expressive the function is, this is going to be larger. So this is kind of your generalization, right? So this is the error that you see on the data, and you want this to be very, very small, which means that what you've seen on the training data is about what you'll see in the future. But if you're using a very, very large hypothesis space, then what is the intuition? If your hypothesis space is very, very large, it's actually very easy to see small error, right? Because, of course, you will find a function that has small error. This is the decision tree case. If you used all the decision trees, your training error was 0, right? Very easy to do. But you're going to pay in generalization, so there's going to be a big gap between your training error and the true error that you'll see. And you've seen this in homework 1. If this is small, then it's likely that this is not going to be 0, because maybe there aren't enough function in H. There's no function that actually gets training error 0. But it's more likely that you'll do better in terms of generalization. There was a question. Okay? So that's one way to say what we've done. And I want to remind you that we've seen this expression or something like this already before. For example, slide 71 in the online lecture, which I put next, basically also had these two components positioned in a slightly different way. So there was the left one that here it's the error on the training data, the right one, which is the generalization, which is a function of how large, how expressive is my hypothesis space. When we saw it in slide 71, we saw it as components of our risk function or error function. We saw it this way. We had one component, the left one, again, is a term that minimizes the error on the training data, and the right one was a term that we wanted, that we used to represent the hypothesis space, and we wanted to push to be simple. So these are kind of two sides of the same coin. This is what drives learning, right? So you have something that really has two components. One of them controls the error on the training data, and one of them controls the generalization. And we've seen it a couple of times this semester. We've seen this kind of bias variance curves, which has the same kind of trade-off, right? So if you have a very expressive hypothesis space, very easy to minimize the error, but who knows what's going to happen in the future, and vice versa. Okay, so basically, this is an insight that we got when we isolated epsilon. I can also isolate m, as we've done before, and then what I'm going to get is the following thing. I'm going to get that an agnostic learner, which makes no commitment to whether f is in H, that is, maybe I'm not expressive enough to minimize, to zero out the errors on the training. Nevertheless, if it sees at least m examples, it guarantees with probability at least 1 minus delta to have a training error less than epsilon, and m is this guy. And notice that it's very similar to what we've seen before, modulo some constants. It goes down with epsilon. Sorry. If I want small epsilon, I need larger m. That's a better way to say it, right? Which makes sense. If I want smaller delta, I need larger m. And it's linear with the log of the size of the hypothesis. So it's the same kind of dependencies that we had before, and the bottom line of what we've done last time and what we've done today is really learnability, because we want this. Spec learning tells us, I want this to be polynomial in the complexity parameters that I have. So the bottom line is that learnability depends on the log of the size of the hypothesis space. Yeah.
So epsilon is like the distance away from the true error? Or?
Is the gap between, in this case, the empirical error and the true error.
So empirical error means like how you form on your train. So
Yes.
and true error means like how it would actually form on this measured up function.
Yes. Before, last time, it was 0 and true error. So it was the same as the error. Because last time we talked about consistent hypotheses that the empirical error was 0. Right? So if you go back to what we said on Thursday, we talked only about consistent hypotheses. So the empirical error was 0. We just did perfectly on all the training data. Now this is replaced by empirical error, or what I called here training error in the previous slide. Yeah.
It's not like the distance from the party function. It's just how far you are away from the actual error you would make it on if you were evaluating the full set. So
It's the error. It has nothing to do with distance in this function space. It's a scalar that says this is what the error that you observe on your training data. Point 1. Is this the error that I'm going to observe also in the future? I hope so, but it's not guaranteed. It could be larger. How much larger could it be? It could be larger as a function of these things. Right? So if you use a very, very large M, what you see on your training data is going to be pretty close to what you'll see in the future. If you see a small m, it's an estimate, but it's not a good estimate of what you'll see. Yeah.
How does this relate to the central limit theorem, or is this like another perspective?
It's another perspective of that, yeah. It's a little bit more refined, right? Because I put here the delta, the epsilon, and the m, and the size of the hypothesis space, right? So it's not just taking statistics, but rather I'm learning into a specific hypothesis space. But conceptually, very, very related. So F-ding bounds is also very related to it, right? It just kind of quantifies it in a more subtle way than the kind of general central limit theorem. Okay, so really the key lesson that I wanted, key two lessons is this one. This is a general statement. I don't need to be consistent, as I suggested last time. I can make error, and I will make error during learning, but modulo this term, my behavior on the training perhaps will not be too far from the real behavior in the future. That's the key lesson. Okay, so that was one of my promise. The second thing is, you see ln of h, which means that h has to be finite. But let's take this example. I want to learn an axis parallel rectangle in the real domain, the real plane, R2. So I have two parameters, and I'm going to tell you that if I'm within a rectangle, it's positive example. If it's outside, it's negative examples. Okay? Makes sense, you know. You can, I don't know, you can be an NBA player if you less than 7'5", and you weigh less than, I don't know, 300 pounds or something like this, okay? Rectangle. And you can also put lower bounds on these, and you'll get a rectangle. So the question is, how do we do it, and can we prove learnability? Now, of course, there are infinitely many rectangles. So what would be your algorithm here? So I'm going to start by showing you some examples. What's your algorithm? Suggestion? Yes?
Probably put just take the max x, y value, like the furthest out diagonally, and just set that as your upper right corner of your rectangle.
You want to say take the max x, max y of the positive examples.
Yeah.
And set this as the top right corner. And you can do the same with the mean and set this as the bottom left corner of the positive example. So basically, the smallest rectangle that surrounds the positive examples. And that's your hypothesis. Make sense? So that's what I'm going to do here. And then I got a few more positive examples, so I'm going to enlarge my rectangle, and so on. So if someone tells me there exists a rectangle, that is, the data that I'm going to show you is consistent with some rectangle, then you can always do this. And of course, the question is, will you be able to say something about how well it's going to generalize? So in fact, you probably don't want to grow your rectangle to be exactly the way I drew here. What would you like to do in real life? Keep a margin. What would you do? Yeah?
Just add some constant to the mid, to the bottom left corner, you just add some more, so you just add a constant to the x, y.
But not just a constant draw from air. I mean, you want to choose this constant somehow.
Some negative examples?
What do you mean, some negative examples?
I mean, like, we could get some points that we know it's not in the concept rectangle.
And
And we can do the margin.
so you want to replace the word constant by
But you just keep expanding the rectangle until you hit one negative example and stop there.
okay, I could do this, but then I will not have margin.
You could use like an average distance between positive and negative.
Split the distance, for example, between the extreme positives and the closest negatives, and this will build the margin. But still, the question is, can we prove something on this? Because before, when we were talking about, say, conjunctions, which is kind of like a rectangle but in a discrete space, we proved that if we will be consistent in the training data, things are going to be good in the future. Can we do this for rectangles? And the problem is that the size of the hypothesis space is infinite, so we need to do something. So the previous analysis that we gave was restricted to finite hypothesis space, and now we want to be able to extend it. Now, everything that we're going to talk about is infinite, but it should be clear that some infinite hypothesis spaces are larger than others. Right? So if I want to talk about rectangles in the plane versus 17-side polygons in the plane versus polygons in the planes or convex polygons in the plane, clearly one class, the polygons is a lot more expressive than 17 sides, which is more expressive than 4 sides. And maybe learnability should depend on that, right? Because if for the same data, you would tell me that I can use any convex polygon, maybe I'm going to learn something else, and maybe something bad or something good would happen as a function of this. So that's the concept that we want to talk about today. So we need a measure of expressiveness of infinite hypothesis spaces. And the measure that we're going to develop is something that is called the VC dimension for Vapnik-Chervonenkis. And we'll see that it's actually completely analogous to the size of the hypothesis space. or in fact, it's going to be the log of the size of the hypothesis space, which is really what we care about. So the key notion in order to discuss expressiveness of function spaces is this notion of shattering. The idea is that you're giving me a bunch of points, and the question is, given a bunch of points like here, I can annotate them, I can label them many, many different ways. Right? I can choose any subset, say these are the positive, the rest are the negative. Right? You can do it in many ways as a function of the size of the space. In some subsets, or some ways of splitting this data set, I can separate with my function class, and some I cannot. And this is going to be the notion of shattering. So let's start with a very simple example. So let's assume that I have 2 points. In this case, the one with the arrow to the top is the positive example, and the one at the bottom is the negative example. I can take a linear function, and this linear function agrees with this function, right? Here is another way. I can take the same 2 points and say the bottom one is positive, and the top one is negative. I can also use a linear function to separate it. There are 2 other ways to label these 2 points. I can say both of them are positive. I can say both of them are negative. And in all 4 cases, I can use a linear function to agree with this labeling. On the other hand, with the many points that I showed before, I can label them this way. Can you see the 2 colors? There are supposed to be 2 colors. For this way of coloring it, above the line you see dark red, and below the line you see some kind of a yellow. For this type of labeling, a linear function works. But on the other hand, if I label it this way, can you see the colors? Then a linear function is not going to work. This one or this one or this one. I'm going to try multiple linear functions. None of them agrees with these labels. With this labeling of the functions, I need a function that is a lot more complex than linear function. So that's the idea that I want to convey here, right? So as a function of the number of points grows the number of possible ways of labeling. And with that grows the complexity of the function space that I need in order to agree with this labeling. So let's define this properly. So we define the notion of shattering, and we say that a set S of examples is shattered by a set of function, capital H, if every partition of the examples in S into positive and negative examples, I can find a function in H that agrees with this partition. That is, that gives exactly these labels to the examples. And the intuition is just as I said before. If I have a large set of points, there are many, many partitions, and therefore I need a large set of functions to agree with this partition. So let's start playing with some, yes?
Would the function in H that gives labels on the examples, would that be a linear function?
No. So H is any class of functions.
Okay, so it doesn't have to be.
So as we'll see, sometimes linear functions are not going to be sufficient. So let's take some examples. Here is a class of function. In this case, the class of function is defined by 1 parameters. These are left bounded intervals on the real axis, interval 0 to a. Okay? So positive example are between 0 and a, negative example is outside a. So now the question is, how many points can I shatter with this set of functions? If I give you 1 point, it can be positive, it can be negative. Can you shatter it with this class of functions? If the point that I give you is 5, give me a function that makes this point positive. A equals 6. Give me a function that makes this point negative. If I give you 2 points, can you shatter it with this class of functions? So I have 2 points. How many ways do I have to label the 2 points? Let's say that the points are 1 and 2 on the real axis. I can make both of them positive. Can you do it with this function?
Yes.
I can make both of them negative. Can you do it with this function?
Yes.
I can make the 1 positive and the 2 negative. Can you do it? You'll choose 1.5. A is 1.5. That will do it. I want to make 1 negative and 2 positive. Can you do it with this class of function?
No.
Cannot. So not all the labelings of these 2 points are realized by this class of functions. So this class of functions cannot shatter 2 points. Okay? When I say shatter, I mean all the labelings. So 2 points have 4 different labelings, and I cannot shatter all of them. I cannot shatter it with this class of functions. So now let's move to a more expressive class of functions. Now I have a class of functions that is defined by these 2 parameters, a and b. 1 point you can do. 2 points, can you do? What about 3 points? 3 points, how many labelings are there on 3 points? There are 8 labelings, 2 to the 3. I can do all positive, all negative, 1 positive, this positive, this positive, this positive, and so on. The easiest way for you to think about it is I have 3 points. I can choose a subset of these 3 points, make them positive, the rest negative. How many subsets are on 3 points? 2 to the 3. Okay? So can I shatter 3 points? What is the problem? Why not? Yeah?
You could have like 1 be positive, 2 be negative, 3 be positive.
So the middle one, if I choose it to be negative and the other positive, no way that this class of function will do it. Right? Everyone agrees? So what we've shown is that all sets of 1 or 2 points can be shattered, but sets of 3 points cannot be shattered. It's sufficient for this statement to be true. Sets of 3 points cannot be shattered. The reason is that there exists a labeling of this set that cannot be realized using a function in this class. No function in this class is going to do it. Okay? And this yellow thing here was just to remind you that even though I'm drawing everything geometrically here, this is really defining a set of functions, right? Everything between a and b is positive, outside is negative. So it's a set of functions parameterized by a comma b. Okay, so we agree on this. Now we can move to linear functions. Half spaces in the plane. We're going to do only the plane here. And again, we can think about it. 3 points. What do you think? Can you shatter 3 points using linear functions in the plane? You'll have to imagine combinations, 8 ways to... No. Okay, why not? Okay, so you're thinking about points on the line, which is okay. In general, I want to think here about points in the plane, but it's okay. If the points are on the line, it's a special case. So what are you saying? You found 3 points that I cannot shatter. Everyone agrees? However, can you find 3 points that I can shatter? If the 3 points are not on the line, not on one line, you would agree with me that I can shatter them with linear functions in the plane, half spaces in the plane. Everyone agrees? So there are sets of size 3 that can be shattered. Remember that. So what about 4 points? What did you say?
I said there would always be like a set that can be shattered.
Oh, not true, not true. So let's take 4 points. What about 4 points? Can you shatter 4 points? Clearly, if it's on the line, if it's collinear, you cannot shatter sets of 4 points. No, okay, good. So the claim here, what if they are all positive? What does it mean to shatter? To shatter means I gave you 4 points, but you need to consider all 16 labelings. You cannot shatter 4 points on one line. That has to be, you have to agree with me on that. So shatter means all labelings, okay? You fix the set of 4 points, they have 16 labelings. There is at least one labeling or more that you cannot realize with this set of functions. Yes?
I guess I'm a little confused because I thought we established for 3 points that there is a like labeling that cannot be shattered.
No, just a second. So for 3 points, what we established is that some sets of points can be shattered, and some sets of points cannot be shattered. You agree? For 4 points, so let's finish the case of 3 just to make sure. 3 points, this is my set of functions. It so happens that if I put all the 3 points on the line, I cannot shatter it. Everyone agrees? If they are not on a line, they're in a general position, I can shatter it. So the bottom line for 3 are that there are sets of 3 points that can be shattered. Now let's move to 4. Yes?
If I have 2 lines, and I have a plus, minus, minus, plus, I won't be able to shatter it.
Okay, so for 4 points, okay, so by the way, this is the point that we just mentioned before. Not all sets of 3 can be shattered, but sets of 3 can be shattered. Now, when we move to 4, my argument is going to be that no set of 4 points can be shattered. So we can think about it in 2 steps. First of all, think about the case that if 3 of the points are on the same line, clearly you cannot shatter. You know, take the middle one and label it differently than the others, and you see that you cannot shatter. Okay? Now, if no 3 are on the same lines, so now I have 4 points in the plane, and my argument is going to be, what I can do is I can build a convex hull using these 4 points. Okay? So now I have a convex polygon lying on these 4 points, and my claim is that if I alternate the labels, I cannot shatter. Think a little bit about it. I don't have a picture for it, but there are 2 cases. One case, there are 3 points that are collinear. You would agree that I cannot shatter. Case 2, there are no 3 points that are collinear. In this case, I'm going to build a convex hull on these 4 points. And if I alternate the labels, you will see that one line, one hyperplane, is not going to leave 2 of them, 2 positive on the right side and 2 negative on the other, or vice versa. So I cannot shatter. So what is the argument? 1, 2, and 3 are okay because there exist sets of size 1, of size 2, and of size 3 that I can shatter. But no set of 4 points can be shattered. And so it's important for you to keep the quantifiers here in place, because everything depends on the quantifiers as I move to my next definition. The question there?
Then
No. Take 3 points in a triangle. I can make all of them positive and all of them negative. That you agree. I'll just put the line there. If you want this to be positive and the other negative, I'll put the line here. For each one, if you want one to be positive and the other to negative, I can separate it with a line. So what is the problem? With 3. With 4, think about them sitting on as a square, the nodes of a square, the vertices of a square, and then if I alternate the labels, on the diagonal I have 2 positives, and on the other diagonal I have 2 negatives, there's no straight line that will do all the labeling, that will do this labeling, okay? So think about it. So there are 2 things you have to think about it here. One is the simple geometric problem, that is just an example here. Think about it and convince yourself that for 3, there is a set of 3 points that can be shattered. By shattered here, all 8 labeling, for all 8 labeling, you can find a linear function that is consistent with it. On the other hand, no set of 4 points, all the 16 labeling that you can do on it can be realized with this linear function. Yes?
Is the difference between being shatterable and being linear separable just that for being shatterable you have to work on all the possible labels?
So it's, I'm worried that it will be confusing to relate them, but let me try. Linearly separable is, there is one fixed set of points, and it has its labeling. Okay, fixed labeling for this set of points. And now the question is there a linear function that realizes this labeling? Put it aside. Shatterable. I have a set of points. I'm going to consider all possible labelings on it, and for each one of them, I'm going to ask, is it linearly separable? But this is only when this is my class of functions. Tomorrow, I'm going to invent another class of functions, right? So for this class of function, yes, I can use linearly separable as a subroutine in my shatterable definition, okay? Okay, so now, so the important thing for you is, one, to put aside the geometric problem that we solve and keep at the center the quantifiers. And what are the quantifiers? This is what I'm going to emphasize when I'm defining here the notion of VC dimension. So, of course, if I have all the function in the world, which I call here an unbiased hypothesis space, I can shatter all my space. Any number of examples that you'll give me, I can shatter. Right? Because once you give me a labeling, I have a function that agrees with this labeling, because I have all the functions in the world. But now that I don't have all the functions in the world, I only have functions that are intervals, or linear functions, or quadratic functions, like squares, like circles or ellipses, or any restricted class of functions. Now, not all labelings are going to be realized using this class of functions. Everyone agrees with that? And now, I'm going to quantify this. I'm going to quantify the expressivity of this class of functions using the notion of shattering and how many points can I shatter. So the intuition is that the larger the subset X that can be shattered, the more expressive the space of function is. That is, it's less biased. Okay, so let's define. We're going to say that a set S of examples is shattered. Okay. So this is actually what I said before. I'm repeating. A set S of example is shattered by a set of function H if every partition of the examples in S into positive and negative examples, I can find a function in H that gives exactly these labels to the examples. Now, the VC dimension of H is the size of the largest finite subset of X that is shattered by H. And this is where I need the quantifier. So let's, so one clarification, even if only one subset of this size does it, I still count it, right? It's the largest subset of X that can be shattered by H. So let's go back to the example that we've seen. So really there are two steps in order to prove that the VC dimension of H is D. What are the two steps? First, I'm going to say, if there exists a subset of size D that can be shattered, I'm at least D. I'm D or larger. Second step, if there is no subset of size D that can be shattered, then it's less than D. So if I know these two, I now know that it's equal to D. Okay? Again, first step, if I found a subset of size D that can be shattered, I know that it's D or above. If I can show that no subsets of size D can be shattered, then it's less than D. These two together are going to be used. So let's go back to the example. For the half interval, I said in 1 point it works. For 2 points, I argued that no subset of size 2 can be shattered. Remember? We took 2 points and we said if you take the smaller one, the 1 to be negative, and the 2 is going to be positive, no way you can label it. So for any 2 points, there is a labeling that is not realized. So it cannot be shattered. Intervals defined by 2 numbers, A and B. For 2 points, I gave you 2 points, and you managed to shatter. When I gave you 3 points, no set of size 3 could be shattered. Because when you label the one in the middle negative and the other 2 positive, there's just no function in this space that can realize this labeling. Half spaces in the plane, the VC dimension is 3. 1 point, easy. 2 points, easy. 3 points. There is a set of size 3 that is shatterable. True, not all of them, but look at the definition. There is a set of size 3 that is shatterable. Just take a triangle, but no set of size 4 is shatterable, and according to this definition, if you put 3 here and 4 here, you will see that VC dimension is 3. Questions on that? Yeah.
So we have to define the sample space or instance space first before we can talk about the VC dimension.
Of course, you always have an instance space, which is the set of examples that you have. On top of it, you define a set of functions. That's how learning works, right? I have a notion of instance space, set of examples. On top of it, I have a set of functions, which are going to be the members of H. And now I can talk about whether H, what is the VC dimension of H. Okay? Yeah.
What does the half spaces in the plane mean?
Linear functions in the plane, I call them half spaces because they cut the whole space into 2 pieces, above the line and below the line. So this is a term. Okay, so thanks for reminding me. So I don't know if people have seen this term. Linear functions in the plane are called half spaces. They're also called hyperplanes. They're also called linear functions. Okay?
And is the half space defined for a 2D dimension, or is this 3D?
So I talked about 2D. And I showed that for 2D, the VC dimension is 3. For 3D, you'll see that it's larger. In fact, in general, the VC dimension of hyperplanes in the n-dimensional space is going to be n plus 1. So when we learn linear functions in an n-dimensional space, the VC dimension is going to be n plus 1. But a little bit harder to prove, so we prove the case of n equal 2. Questions? Yeah.
What is the value in knowing the VC dimension?
Okay, so let's move on, and hopefully it will answer your question. Okay, so far it was just a game in kind of understanding some combinatorial parameter of function spaces. Here is why it's important, and I'm not going to prove it. So exactly the same theorem that we showed before, given a sample D of size m examples, if we find H in H that is consistent with all m examples, and this is m, then with probability at least 1 minus delta, H is going to have error less than epsilon. So it's exactly the same theorem we proved before for consistent hypotheses, only that there are some constants here that we don't care about. And the key thing is that the VC of H stands here in place where log of H stood before. Okay? So learnability that we said before depends on definiteness, or in fact, polynomial of log of H, now depends in the general case on VC of H. That's why we care about this. Okay, so this is where, now here is a question. What if H was finite? What will happen to this statement? Will it be consistent with what we showed last time, or will it be very different? What's the relation between the VC of H when it's finite and the size of H? So let's assume that I tell you that the VC of H is M. Okay? Let's see, what does that mean to you? Yeah?
Is the label either positive or negative only?
Yeah, so we are only talking here about Boolean functions. All this theory is for Boolean functions, yeah.
So H can separate up to 2 to the m subsets.
Okay, so let's just say it again. So I told you that the VC dimension is M. That means that there are 2 to the m dichotomies or partitions that H can separate. That's what you're saying. Why? It's from the definition of shattering. I gave you, I said VC dimension is M, which means that all possible partitions on M points can be shattered. How many partitions are there on M point? 2 to the M. So what does this mean about the size of H? At least 2 to the M. So that's the relation between the VC dimension when the class is finite. Let's just say it. Now it's written here. So we talked about case of finite hypothesis spaces, and we plugged here in this formula log of h. Now, instead of log of h, I put here VC dimension, and I want to go back and see whether these two things are consistent. How do I check whether they are consistent? I'm saying, okay, let's assume that this guy is equal to m. What does it mean? It means that I can shatter m examples. If I can shatter m examples, what does it mean? It means that I looked at all the partitions of these m examples, and there are 2 to the m like this. And for each one of them, I found a function that realizes it. Right? I took all of them to be positive. There is a function that does it. I took this to be positive and the rest negative. There is a function that does it. I took these two to be positive and the rest negative. There is a function that does it. So all combinations I found functions, which means I had at least 2 to the m functions in H. So the log of H is greater than m, which is the VC dimension. So that's the relation, and hopefully this also allows you to think a little bit more about what is VC dimension and why it is important. So concept 1 that we cover today is, we talked about VC dimension, we defined it. It's subtle. You have to understand the quantifiers. So go to the 3-4 example and make sure that you get this, and realize that the definition calls for 2 steps. One step that says, well, I shattered, so I'm at least a D. But for the next step, I cannot shatter, so it's no more than D. Okay, so now let's go back to the problem that we started with, learning rectangles. I want to show that the class of all rectangles in the plane is Spec learnable. So 2 steps in Spec learning. One of them is the sample complexity. And in this case, because it's infinite, I'm going to talk about VC dimension. And the second step is going to be, give me an algorithm. First step, VC dimension. So I'm claiming that if I take 4 points, some instances of 4 points can be shattered. So for example, these 4 points can be shattered. If you think about it, there are 16 different labels. 1 positive, 3 negative, there are 4 like this. 2 positive, 2 negative, there are 4 choose 2 like that, and so on. 16 altogether, and you can play with it and you'll convince yourself that all labeling in this configuration of 4 points are realizable. Of course, there are set of 4 points that are not. If they are going to be all on one line, not going to do it. But I don't care about it. All I care is that there are sets of 4 points that I can shatter. Okay? Now I already know it's at least 4. And I have to move to 5. And my argument for 5 is going to be no. That is, no set of 5 points can be shatterable. Anyone want to try an argument? Yeah.
I mean, you can use this as kind of an inspiration to take the outer 4 points and do the convex hull thing you were describing, and have there's always going to be one in the middle. You could argue like that, and then you have to consider cases where some are collinear, some aren't. But
So that's a good start. So it could be that there's nothing in the middle, but that means that the 5th point is also on one of the sides. So I'm basically taking the x min and max, the y min and max. So I generated this rectangle. And if there is one in the middle, good. What will I do if there is one in the middle? I'm going to choose it to be negative and the rest positive, and I convince myself that this labeling is not realizable. And the same thing if this 5th point is actually on the side. So the x max, for example, is the same for more than 1 point. And I can, again, choose different labels for this. So basically, the argument is there can be at most 4 distinct extreme points, smallest or largest along some dimension, and these cannot be included, that is, cannot be labeled plus, when the 5th point is labeled minus. Yes?
Sorry, just something small. When you say convex polygon, it means the angles on the inside are all 90 degrees or less?
Convex polygons means that, actually I don't need to use the word convex here, but what I mean is that when I connect 2 nodes, the line between them is inside the polygon. Maybe it's equivalent to what you said, but I have to think a little bit about it. So take every 2 nodes and connect them, the line between them is inside the polygon. So I don't have something like an angle polygon, where I take the 2 nodes and I connect them and it's outside. But you don't need the notion of convex for here. It's just take the extreme. So basically what I showed here is that the VC dimension is 4. We showed that it's at least 4, that was easy. A little bit harder to show that it cannot be 5. And therefore it's exactly 4. So we are done with one step in proving that something is learnable, because from the perspective of sample complexity, everything is fine. The second thing is learning algorithm. Can we give an efficient algorithm? And in fact, you already gave an efficient algorithm when we started, right? We basically said, find the smallest rectangle that contains the positive examples. And you're done.
How do we go from the step where you can where the VC is 4 to its pack learnable?
Oh, because we said in the definition of pack learnable that if the sample complexity is polynomial in the complexity parameters, then it's pack learnable. And I gave this bound, which is this. Right? So if the VC dimension is in fact finite, I don't need it to be 5, because of this bound that is M is polynomial in 1 over epsilon, 1 over delta, and VC dimension, you're done.
So if the VC dimension is finite, then
In fact, this is enough, yeah. But it's more interesting to try to compute it. Okay, so basically we are done. So to summarize, we define VC dimension. You know how to make an argument on what is the VC dimension of something with these 2 steps, greater than D, less than D, or D plus 1. And we use this also to make 2 steps argument for whether something is learnable or not. So just to summarize what we've done, what I said so far, and in fact, when I gave you the dependence of the number of examples, or how many examples are needed so that you'll be quiet and happy and say, okay, I learned this function and I got this small error on my training data, I know that it's going to be good in the future. So we developed this bound on M. This was an upper bound on M. And it could be a very, very loose bound, but at least it's something that tells you, don't worry, if you've seen enough examples, things are going to be good in the future. It turns out that you can even prove a lower bound on this, not that you should care, but basically you can say, you know what, you have to see at least these many examples for it to be good in the future. I'm not going to go into this bound, but it's good to know that one can prove something like this. So actually, it's not going to be the case that, you know, you can see 3 examples and everything is going to be okay. Maybe you'll be lucky with 3 examples, but in principle, one can show that as a function of the hypothesis space you're using to learn, there is also a lower bound on how many examples you need to see. So to summarize what we've done, we talked over the last lecture and a half or two about a PEC framework that gives us a model to think about what can we say about learning algorithms. We talked about sample complexity, that really is a function of the size of the hypothesis space or the VC dimension of the hypothesis space, and said that really as a function of this complexity parameter, we can say something about whether a hypothesis space is going to be learnable or not. We said something about the gap between the error that you see in training and what you can expect to see in the future. And we saw this true error is really a function of what you see in the training plus something. And this something depends in a natural way, in an intuitive way, on the number of examples you've seen, the error epsilon, and the delta, the confidence with this is going to happen. We didn't talk a lot about computational complexity. If you look at the hidden slides, you'll see that I talked a little bit about it there, but I kind of shoved this a little bit because I really wanted to give you a taste of the fact that one can actually explain why things are going to work in the future. It's not just that you run an algorithm and it so happened that on this data it worked. Who knows what's going to happen on another data? It's actually that we can prove under realistic assumptions on the hypothesis space that you're using that, and the number of examples that things are going to be good in the future. Now, there are many, many additional things that can be studied using this framework. You can study learning with noisy data and understand what are the degradations that could happen and even quantify them as a function of the different types of noise. You can think about learning under specific distribution. We were very, very general in our definition. We said any distribution, as long as training distribution is the same as evaluation distribution. You can think about learning many, many interesting hypothesis classes, deterministic hypothesis classes. I gave the simple example of KCNF. You can think about learning probabilistic representation under the same framework. You can think about neural networks. You can think about finite automata, for those of you who know what finite automata are. You can think about active learning, sort of interactive modes of learning, and all these things can be analyzed using this tool of computational learning theory. You can even extend it to think about what is called PEC Bayesian theory, where I talked about probably approximately correct PEC, but you can also impose some distribution over the hypothesis space and be Bayesian, which we're going to talk a little bit about after the spring break, about how you choose a hypothesis from this class. It's not going to be any hypothesis that is consistent with the data or almost consistent, but rather you'll have some probability distribution over the function. So there are many, many other extensions. And really the important insight is that these theoretical results give some understanding of when learning works, how learning works, and give you an idea of how to select models. That is, which hypothesis do I want to use and when. And they also helped us develop and understand various algorithms. So support vector machine, which is what you played already in your homework, but we're going to understand it better in the first lecture after the break, is an algorithm that was driven completely by this VC dimension theory that I talked about before. So the idea was to develop a linear learning algorithm, kind of like perceptron, but a one that selects the hypothesis, the linear function, so that to minimize VC dimension of the hypothesis class, because we know that small VC dimension is good for us. We know was also an algorithm that actually was driven by a theoretical question. Boosting, which is the lecture after SVM, is a very, very important learning algorithm that was also driven by a learning theory question or challenge, if you want. And regularization, all these concepts really came as a direct understanding of this theory. Questions? Yeah.
What does it intuitively mean for something to be pack learnable?
It means that if you did well on the training data, you're going to do well on the test data. This is basically justifying generalization, as if and quantifies, justifies and quantifies generalization as a function of the complexity parameters that we have.
So the number of like you said, the number of examples has to be polynomial. Like the number of examples that you need to see have to be polynomial.
In the complexity parameter. So you give me an epsilon that you're willing to incur, and a delta, which is a confidence parameters. The number of examples has to be polynomial in these,
And then we say it's pack learnable.
under this condition. But we proved that this is going to be the case. So that's the definition. And then we gave a theorem, the Occam's razor theorem that we showed last time, and showed that, yes, M is going to be a polynomial function of 1 over epsilon, 1 over delta, and the size of the hypothesis space, or today we replace it by the VC dimension of the hypothesis space.
So what's an example of something that's not pack learnable?
So neural networks, by the way, are not pack learnable. Set of all Boolean functions is not pack learnable. Decision trees are not pack learnable.
Because the hypothesis space is like
It's too large.
So even the VC dimension is not like.
The VC dimension of decision trees is going to be exponential,
Yeah.
doubly exponential, in fact, in the instance space. So just think about the set of all Boolean functions. How many Boolean functions do we have on n variables? We talked about it at the beginning of the class. It's 2 to the 2 to the n. Log of this is going to be 2 to the n, not polynomial. So you have to restrict your hypothesis space. You cannot hope to learn using a hypothesis space that is all the Boolean function. That's one trivial conclusion from pack learning theory. You have to restrict your hypothesis space. Okay? And again, I didn't go over the negative results. There are 2 slides because I wanted to get to the positive results, the VC dimension theory, but it's in the slides if you want to dive more into it. Yes?
Will today's material be very included?
Yeah, what I did today will be included, all up to this last question. So exam on Thursday. If you came late to the class, look at the slides. They are on the web. People that are A to K inclusive are not going to be here, but are going to be in another room that I've written on the slides. So go there. Be there before 1:30 next Thursday. Say it again.
Why would you ever use something that's not pack learnable? So this is, you said they're not pack learnable.
Because maybe you have a small feature space
Or I was thinking
and you don't care about using a lot of examples and no guarantees.
So if
Because-
your training data is like really close to the actual, like what you're going to see in the future, then like you don't care if it's pack learnable, right? If you have like a lot of data.
So the issue is this. It's not really an all of data. So pack learning is a worst case thing, right? So maybe really what I have is very, very simple concept. And the distribution that I whatever the
Those negative
definition of natural
examples.